What I want to do is first I'll just show you a kind of a typical VPython program and what it's good for. Then I'm going to write a program in front of your eyes, line by line. You don't have to take notes on that or anything. For one thing, it's going to be in the recording that Marco is going to make. But also, I'll post a link to the program that you can then run again. And I will use that line-by-line construction of a program to give you an overview of the various kinds of capabilities that are built into VPython. Now, what you've seen so far is that you can display a 3D image, and you could even move things. But there's also, so I want to show you what are the various kinds of objects, 3D objects that are available, and something about how you make graphs, including live graphs, including scrolling graphs, and how you can very easily make so-called widgets, buttons, sliders, that kinds of things to make it easy to interact with the program. But to start off this, first I'd just like to show you a running VPython program. Here is a binary star program, and with the mouse I can rotate the view, I can zoom the view. If I hold down the shift key, I can pan back and forth. And it's obviously in 3D. And here are these two objects attracting each other gravitationally and leaving trails behind. And normally to write such a program using any programming language, including Python, would require pages and pages of extremely arcane code. And here is the entire program, and I'm going to go through it line by line to show you how this all works. So this is really pretty unprecedented for such a short program to do that much. So first of all, with this first line, we simply define the Newtonian gravitational constant, which we'll be using. We create a sphere object, which we'll call giant. And this sphere object has various attributes. It has a position attribute, which is a 3D vector. And VPython handles 3D vectors very easily. You can add them, you can subtract them, you can take the magnitude, you can make unit vectors out of them, you can do dot products, cross products. So it has built in all of the standard vector algebra, which is a great convenience if you're working with 3D objects. Specify a radius for this sphere object, specify a color for it, that it be red. Say that make trail is true, namely, when this sphere object gets moved, it should leave a trail behind itself. So you don't have to deal with that, it's just going to happen. And you can specify a trail type to be points. The default is a smooth curve. You can specify an interval, update that curve only every 10 times, and how many to retain, so you get a kind of a comet-like display. So the sphere is an object, it has attributes, and giant is an instance of the class sphere, okay? It's being Python, you can specify additional attributes of your own for giant. So giant.mass is the mass of the sun, actually, and giant.p is the initial momentum, which is the giant's mass times the vector, a vector chosen for its velocity. Then we make another instance of the sphere class with its own position, radius, color, make trail is true. By default, it's going to leave a curve rather than dots, intervals and retains, and name that dwarf. And the dwarf has a mass of half the mass of the sun and a momentum that is the negative of the giant's momentum. Therefore, the total momentum of the system is 0 and the center of mass will not move. That's why this binary star wasn't moving through the universe, it was just sitting there. Then choose a time interval of 10 to the 5th seconds, and while true, run this loop no more than 200 times per second. No matter how fast your computer can run, this says don't do more than 200 iterations per second. And it has another usage as well, which I'll come back to in a moment. The next thing is we're going to calculate a position vector that points from the giant star toward the dwarf star. And we're going to calculate a force using the Newtonian formula, namely the big G times the mass of the giant times the mass of the dwarf times r hat. What's r hat? Well, a vector r has various methods that include and attributes, including the hat attribute, which is, say, make a unit vector. Namely, take the vector, divide it by its magnitude. So that gives you the direction of r, and we'll divide by the magnitude squared of that vector. So there is, oops, didn't mean to move it. There is the calculation of the force. Now, the giant's momentum, we can predict the new momentum will be its current momentum plus the impulse, force times dt. For the dwarf, it's the same force but in the other direction. So it's got a minus f dt. And now, having updated the momentum, we want to update the positions. And ideally, we want to do that with the average velocity. It turns out, and it's not at all obvious, that in first order integration, which is all we're doing here, the particularly good job of doing it is to calculate the force, update the momentum, and use the new momentum as a surrogate for the average velocity. That, in fact, turns out to be better than, say, taking the arithmetic average of the old momentum and the new momentum. And this is called Euler-Kromer first-order integration. And it does a remarkably good job for a given delta t of preserving energy, conserving energy, and also conserving phase space, interestingly. So we're going to take the new giant's momentum divided by its mass, multiply by dt, and that is the 3D displacement of the giant. So if we add that to its current momentum position, we get its new momentum. And similarly for the dwarf, we take the dwarf's momentum, divide by the mass, gets its velocity, multiply by dt, that's the displacement, add that to its current position, and you get the new position. Now, looking at this loop, normally, if you're writing in some other language environment, there would be a very large number of extremely arcane statements to get 3D displays of these moving objects. Where in this loop are there any graphics statements? So I'm hoping to hear great silence because you don't see them there. They're not there. The rate statement does two things. Rate 200 says, in order that the thing not run too fast for you to see the animation at all, don't do more than 200 iterations of this while loop per second. So that's one of the roles that this rate function performs. It does something else. In the meantime, while it's checking to see that you don't do more than 200 iterations per second, it's also looking to see whether a 60th of a second has gone by since the last time we painted a 3D picture on your screen. That picture is being drawn by a library called Webgl, which is built into the modern browser and has been there for, I guess, close to 9 years now, maybe 10 years. It's a 3D library. It's based on an earlier library, OpenGL, which is still used. OpenGL is an open source version of a 3D library, which, and WebGL does its job. WebGL is basically a little sister of OpenGL, and OpenGL uses the graphics processing unit built into just about everybody's computer now to do the 3D visualizations very fast, because the GPU, so-called graphics processing unit, has built into it hundreds, even thousands of little computers that can work in parallel to figure out what color all the pixels should be in the scene. So this rate statement, every 60th of a second, calls upon WebGL, which is part of the browser, to paint a 3D image using the attributes of the current attributes of the objects that have been created. Well, we created two objects, both of the sphere class. They have different positions and colors and so on. And compared to a 60th of a second ago, they have new position attributes. So when GLL goes to paint a brand new picture, it starts from scratch. Every time it paints a picture, it starts from a black screen, and it generates the 3D images based on the current attributes of those objects. So the graphic statements in this while loop are essentially these statements, which look like and are physics statements, but because you've modified the position attributes of the giant and dwarf instances of the sphere class, you get an animation. Now, let me pause for a moment, and Marco, you might have to help me because I won't necessarily see everything. Are there questions about what I've just shown you as a warm-up?
I mean, there are no questions in the chat, guys. If you have any question, just unmute yourself and ask.
May I have a question? I'm just wondering why you completely explained it, but would you please again tell me why the rate is exactly 200? Why don't you increase it?
I'm not sure I understand the question. Let me say immediately, I have a hearing impediment, and so and the audio isn't perfect. So I didn't fully understand the question, and that may be just a hearing problem. Maybe Marco, you can help me too.
Yeah, I think that the question is about this rate statement.
Yes.
And the question is, why don't you increase it? I mean, I guess it depends on how fast you want the things to move.
Right.
Right?
Yeah. So for example, let me make it 2,000 instead of 200. Okay. And let's see what we see.
You left it at 200, I think.
You're right. Thank you. Okay, so that's the effect of the rate statement.
So you make it 20, you make it way slower, no? But it's just for yeah, exactly.
Yeah, does that answer the question? Was that the question?
Yes, it was the question, and thanks for the answer. Okay. Yeah, that was great, thanks.
You're very welcome. The issue is that computers are extremely fast, and this very small amount of code here takes, microseconds. And so basically you have to slow it down. Now there is a
question in the chat here. Sorry to interrupt you.
Oh yeah, sure.
And that's actually a good question. It's like where we can find an inventory of functions in VPython online? So
at glowscript.org, let me write it. glowscript.org, click help. And in fact, I'm at glowscript.org at the moment, and I'll say more about that in a moment. And if I click on help, what I see there is stuff like choose an object that you're interested in. Maybe you want to know how to draw a cylinder, and here is all the information on how to draw a cylinder. Maybe you'd like to know what are the mechanisms for working with vectors, and here are all the things that you can do with vectors, but they're basically what you would expect, plus some additional ones like converting between degrees and radians. That there's cross products, there's dot products, difference in angles, unit vectors, magnitudes, equality, inequality, and so on. So that's where you get the information. And this provides an excuse for me to say something more about where I am. I'm currently at glowscript.org, if you notice up here. And I'm writing a Python program sitting in a browser, not using, I didn't have to install Python, and we'll see later, I could be working in Jupyter Notebook. I choose to be working here at the moment because I'm just more comfortable there than I am in the notebook for this kind of use. I'm not making notes. At glowscript.org, you're sitting in a browser, you log in, you get to your files. Here's my file. You saw me editing and so on. You saw me running the program. When I click run the program, the Python code is transpiled to JavaScript code. In fact, I can show you what that JavaScript code looks like if I comment this out. Here is pretty ugly looking stuff. You can recognize some of it. There's some stuff there that you see a mass and a momentum and so on. This is the JavaScript code that is generated from the Python code. And why is that being done? Python doesn't run in a browser. JavaScript runs in a browser. So I use a tool called RapidScript NG, which does a very efficient job of transpiling Python to JavaScript, which does run in a browser. You can also export this JavaScript code and stick it in your own web page, and it'll run there because it's just JavaScript. Now, I hasten to say that this same program will run in Jupyter Notebook. There you say, instead of saying GlowScript 3.0 VPython, you'll say from VPython import star or something equivalent. And the exact same syntax works there. And the way it works there is that you install Python, you install the VPython module, and when you're running your program, there's a Python code in that VPython module that sends messages to a browser page it picks up, and over there, it sends instructions over to the browser where there's a JavaScript program that runs the GlowScript library to paint the pictures. Any questions on any of this that I rattled off quickly? Now, I'll mention that a value for some of us who are interested in introductory physics is that it turns out, before there was this GlowScript version of VPython, when Rishabhai and I introduced computational modeling into the intro physics course taken by science and engineering students, it used to be that students had to install Python. They had installed the VPython module. If they were on Mac, they had to install an update to something called TCL. Any of those installation procedures could fail in strange ways. We had not appreciated what a huge barrier that was to freshman students, almost all of whom have never written a program before, and they've certainly never installed software. And when it became possible to send them to glowscript.org, where they didn't have to install anything, they just wrote programs and ran them, there was a huge rise in enthusiasm for VPython, which had been much bigger barrier to them than we had realized. Now, obviously, in a course like what you're taking, and much higher level, you want to be using professional tools like Jupyter Notebook, Jupyter Lab, and so on, and have access to all the Python libraries, which are very extensive. But in the intro physics course, this is sufficient and more than sufficient for our needs. The downside of working in this browser-based environment is that since it's really a kind of a thin wrapper around JavaScript, actually, it can't import NumPy. It can't import Python modules because it's a JavaScript environment. So it has its limitations, but at the freshman level, it's great. Other question before I go on?
Yeah, there is another piece of question from the same chat, but that's a simple thing. The question is, where is DT? DT is defined on line 14 in the script. If you look at it, you're aware.
Yeah.
Yeah, it's 1 to the 5, 1 10 to the 5.
Yeah.
So it's a parameter that you put. I mean, these are, I guess that's that you are using kind of cosmological numbers.
Yeah.
Typically you have a small mass, you take a time that is 10 to the minus 5, you know, taking 10 to the 5, because on a cosmological scale, this is like a fraction of a second.
Yes, it has to do with 2 by 10 to the 30th kilograms.
Exactly.
By the way, notice too that doing this iteratively like this vivifies Newton's second law, the momentum principle. It says, take the current momentum, take the current force, let it act through a short time interval dt, short compared to whatever, and iterate, just iterate. Usually in intro physics in particular, you get F equals ma, and there's a solution for a, and there's a solution for x, and it's x is x0 plus x0 t plus a half gt squared and so on. And there's no sense of mechanism. It's just this formula that tells you positions and velocity at some future time. But here there's a very strong sense of mechanism. You can see it. You calculate the force at this moment. You get the impulse for a short dt. That impulse added to the current momentum will give you a new momentum. The new momentum gives you a new velocity, and that velocity times dt added to the current position gives you a new position. So there's a strong sense of mechanism. And interestingly, this is how Newton thought about it. Newton never wrote F equals ma. That's not a Newtonian statement. What Newton talked about was blows, 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 and you get an orbit, which is really quite charming and very illuminating. Okay, so that's the first thing I wanted to show you, just to give you an example, and so that you could kind of see the structure and what this is and what it isn't. Notice that there is no physics built into this, into the VPython module. What is built into VPython is a good understanding of 3D geometry and the tools for manipulating 3D geometries, but it doesn't know any physics whatsoever. And we'll see that again in a moment. Okay, so I'm going to write the world's shortest program here. And what I'm going to do now is I'm going to write what will end up being a moderately sophisticated program, but I'm going to do it a line at a time. And I encourage you not to try to take notes, because it's going to be recorded and the final product will be available to you as well. But if I say BOX left parens right parens, that's a very short computer program. But when I run this computer program, what I get is a 3D box. And I can rotate the camera to look at it. I can zoom in and out. I can move back and forth. And notice too that when I run it, it actually placed the camera in such a way as the object filled the screen. It didn't start out looking that way. Whoa. Where does that all come from? Well, in most 3D programming environments, in fact, in most programming environments in general, you are asked to set up a lot of that stuff. The VPython was created in the year 2000 by a student of ours at Carnegie Mellon University named David Scherer, who was a very powerful programmer, so powerful that he didn't graduate in computer science. He didn't finish his degree at computer science at Carnegie Mellon University because they didn't have anything to teach him at Carnegie Mellon University. And he went on to create not one but 2 hugely successful software products, of which made him a multimillionaire. This is a very unusually powerful guy along many dimensions. Most such powerful programmers are not interested in the problems that novices have. He was. He wondered, is there some way to make 3D animations from a computer program accessible to ordinary mortals? In fact, novices. And he did two things. One was, as you saw, the idea that the redisplaying the display every 60th of a second would be just done behind your back for you. But the other great idea he had was to put in a tremendous number of intelligent design defaults. So for example, if you say, I want to make a box, that could and should and does in this environment imply that, oh, I need to set up a 3D canvas on your browser page because that's where Webgl can do its work. I need to actually create a 3D box by drawing 12 triangles, because that's how Webgl makes triangles. I'm going to, by default, color it white with a black background so you see it. I'm going to check to see how much space is required to be able to see all of the objects you've made, and position the camera in such a way that they fill that canvas. And I might as well turn on mouse controls to let you rotate and zoom and pan, because that would be useful too. And all of those is sort of natural. And by default, yes, a box has a position attribute. By default, I'll put it at the origin, 0, 0, 0. And by default, it needs a color. By default, I'll make it white. By default, I'll make it 1 by 1 by 1 units. So I get something. The typical situation would be I would have to specify a color. I would have to specify a position. I would have to specify where the camera went. I would have to. And this says, look, just do something, and you get something on the screen. And if you want to do something more than that, fine, go for it. But at least you get something, and the camera's even pointed in the right direction. So notice that basically he set things up in such a way that for the novice programmer, navigable, real-time 3D animations come as a side effect of your physics statements. This is really, truly without precedent as far as I know. And it was great. Okay, so that makes a box. But maybe you want to do something fancier. So I am going to go and get something slightly fancier. So I'm going to replace that simple box with this more complicated statement. I'm going to make a box, but I'm going to specify position as a 3D vector at 0, -5, 0. So it's going to be below the center of the screen. I'm going to specify size, length, width, height, which for convenience, since it's a triple, is done with vectors, which means that you can actually manipulate them. So it's going to be 10 wide, 0.2 height, and 10 deep. So this is going to make a floor will be textured to look like wood. And when I run this program, you see that there's this thing down here that's going to be a ball, about a floor on which we're going to bounce a ball. And again, it moved the camera out in such a way that you can see that the whole floor. Okay? So already you see that there's some rather sophisticated capabilities, even of something as simple as a box or a sphere. And you can make them invisible, you can make them transparent, you can do all kinds of things with them. You can have them off in some funny direction, etc. And we'll see some of these things. Next, what I want to do is I want to bounce a ball. So next I'm going to make a ball out of a sphere object, and I'm going to call it ball. So here's a sphere object. Here's its position at -5, +5. So it's going to be above the origin where the floor is below the origin. It has a radius. It has a color. It's going to leave a trail. And it's going to be emissive eventually, but I'm going to turn that off for the moment, and I'll come back to that later. So here's now what our program looks like. Now we have a floor, and we have a ball above it, and it's not doing anything. Oh, and by the way, some lighting was set up so that you can see this stuff, and you can see the lighting of the ball. But I want to make it move, so I'm going to set up a bunch of things here. I'm going to add an attribute to the ball object of a mass, just like we did with the stars. So the ball's mass is going to be 0.5 kilogram, and the ball's initial momentum is going to be that mass times a vector that has a little bit of x component to it. Now when I run this program, of course you don't see anything different because I haven't put in any physics to move that ball. And I repeat, VPython doesn't know any physics. So let's also specify some physics. So we'll put in a definition for little g. And now we're going to set up a while loop. Pick a time zero, a time step of 100th of a second. While the ball position's x component is less than 8, let the ball go. And I will put in a rate 200 like we had before. And I will calculate, put in some calculations here. So I'm going to calculate, I'm going to do Euler-Kromer again. I'm going to calculate a force that is in the negative y direction. I'm going to update the momentum of the ball by the impulse that acted, f dt, and all this is 3D. And I'm going to take the ball's momentum, new momentum divided with its mass as a surrogate for the average velocity, multiplied by t is the displacement, add that to the current position, and I'm not ready for this statement here yet, so take that out again. And so now we should be able to run the program and see a bouncing ball. And there it goes. Oh, huh. Well, I claimed that VPython doesn't have any physics built in, and it doesn't. So it kept doing what we said it should do, and which meant that it accelerated more and more and more and more toward the center of the Earth. So let's put in a test. We'll do two things. First, we'll test, does the ball hit the floor? So if the position, the y position of the floor, if the ball's position is less than that plus the ball's radius, that means it's made contact, right? So if it made contact, let's set the y component of the momentum to be its absolute value, so it heads upward. Now you could also, we could just do it by saying minus, flip it. But it turns out when you're doing iterative things of this kind, that can sometimes trap the ball because you turn the around, and it could be that thanks to even just problems of finite precision in a computer's use of floating point variables, you can actually get stuck in there. So it's better in such a case to actually force it to go upward instead of get trapped. So here now we should see some bouncing because it'll turn around when it's there, and it should also come to an end at some point as we increment the time. Actually, at the moment we're not really needing the time, but we could be using it. Here we're going to stop on a position. If we run this program, now what we get is that, which is rather satisfying. But it is still doing just exactly what we told it to do. We didn't put in a test to see if we'd come to the edge of the floor, but we're getting there. So let me pause for a moment and ask if there are questions about this, which is somewhat what we did before. But questions so far? Because I'm going to make it much fancier next.
I have a question just about where you're headed with this.
Yes.
So you kind of show a ball bouncing with like an elastic collision. What happens if the collision is less elastic? How do you program that?
Well, you tell me. What should I change on line 17?
Well, I mean, you could do absolute value times 0.8 ball.py, but...
Okay, let's try it. Is that what you wanted?
Well, I mean, that's the same, that's the size that I want, but like, dealing with the real world, you're not gonna know like the exact value to multiply the...
That's where the physics comes in. VPython won't help you in deciding what the coefficient of restitution should be for balls of a ½ kilogram mass striking a wood surface. You get to do the physics, if I interpret your question properly.
Yeah.
Yeah, so
Okay.
basically, if I interject, it's basically what we've been discussing on Tuesday, that you have to make your model, and once, you have to, first of all, you have to have some sort of physical system that you want to simulate. Then you have to make your model, and the model is where you have to decide what is this coefficient of restitution, or how large is your box, or your platform, and how heavy is the ball, and so on. And then you have to write the algorithm that correspond to your model. And you do it in this case by using VPython, so that not only you code the physics yourself, but VPython automatically will give you the graphics that shows the trajectories and everything.
Which is a very powerful tool for seeing whether your model even makes any sense.
Yep, exactly.
Like our first model wasn't great when it went through the floor and kept accelerating forever. And also, there's another subtle thing, and I know Marco shares some of his interests here. The model is a model. The best algorithm you can write in the world is only a model. You cannot capture in it, and you may claim that you need not capture in it, the effects that Mars has, its gravitational pull on that ball. So what we physicists study is we make models that are necessarily incomplete. They are necessarily incomplete compared to what happens in the real world. Then we confront the output of our model with what we observe. And maybe we find, oh, gee, we didn't consider quite properly the air resistance effects here, and we didn't even consider them, and we need to put them in there, and we ought to think about how rough the surface of the ball was, all that sort of stuff. It's all approximate, but we try to get as close as we can, and we keep revising our models to try and get closer and closer to what we perceive in reality when we look at nature. And so sometimes people say physics is an exact science. Well, it's exact in the interior of our model making. So this is exactly modeling what we exactly modeled, but what actually happens in the real world is another issue. So in that sense, it's approximate. Our models necessarily are approximate, an approximation to the real world. There's some philosophy here too.
Thank you.
And interestingly, the word model should be prominent in all physics courses at all levels, both undergraduate and graduate, and typically is not, actually. And we often have students coming to us from high school physics. Chris Chabai and I teach intro physics. And they come to us from high school physics believing that physics is exact in the full sense, that making an approximation is not a legitimate move. And one of the things we try to do is make approximations to be an absolutely illegitimate move. It's the only kind of move we have, actually. Okay, let's go further. So this is kind of cool, but it would be nice that if while this thing is moving, there was an arrow showing the momentum. That would be sort of cool. Just as it's easy to leave a trail, it's also easy to leave have an arrow go along with it. I'm going to go back to bouncing perfectly. So what I'm going to do here is something rather unusual. Okay, what on earth is that statement? Attach an arrow to the ball based on the P attribute of the ball object. Now, Paul.P, that's the momentum. So what I'm saying with this statement is, as the ball moves and as its momentum changes, represent that its vector momentum as an arrow tied to the moving ball. And having added that, this is what we'll see. Oh, and the camera even moved back in order to be able to show that. So again, this is an extremely compact, powerful way of adding an important visualization where you can actually see the momentum represented as an arrow. And by the way, there's another odd aspect of this programming environment. We have arrow objects. You can attach arrows. You can also just make an arrow, display an arrow. And an arrow is seen as a representation, a concrete representation of an abstract entity, namely, in this case, momentum. So a vector is abstract. An arrow is a representation of that abstract entity. An arrow could represent something else, or you could represent a vector as a color on a color scale. The more red it is, the bigger its magnitude. There's nothing magic about arrows being used to represent vectors. And it's actually fairly important to keep clear in your head that the abstract vector and its representation as an arrow they're separate things. And interestingly, in every physics textbook, you will see in a diagram, here's this scene that's maybe 2 meters wide, and there's an arrow representing a force of 3,000 newtons and a velocity of 10 to the minus 3 meters per second. And all of these arrows representing those vectors are shown big enough so you can see them. They all have completely different scale factors then. I mean, 3,000 and 2 don't fit on the same screen at the same scale level. So silently, those diagrams have all those abstract vectors scaled before being printed on the page, something that's not widely recognized. It shows up in spades here and makes it easier to talk about the difference between an abstract vector and a concrete arrow, because you can actually make arrows that represent vectors. Okay, so we attached an arrow. That's sort of cool. And I would like the camera not to back up when it gets down there and the arrow, it goes so far below that we can't see it without backing up. So I'm going to say scene, which is the name of the 3D canvas that is made by default for you. You don't have to make one. You can make one of your own, size it and color it, whatever you. But I'm going to make a scene. Auto scale is the operation that moves the camera forward or back to make sure that everything stays on the screen. But I'm going to set it to false once we set this all up, so that now the camera won't back up when that arrow is too big to be seen. Okay, so notice the program hasn't gotten a lot larger. And let's see what else we can do. It would be kind of cool to be able to pause the motion and restart it. So I'm going to set up the following stuff. I'm going to create a function run button whose attribute will be a button you can click on. And there's a run variable, what I'm going to set to false, and I'm going to consider it a global variable, that when you click on it, it'll flip between saying run and pause. And I'm going to specify, create the button object itself that will drive that. So what this statement says is make a button, display it on the screen underneath the canvas we've been looking at. It will say run, and bind that button to a function up here, run button. So what will happen is with these statements that I've added, we'll see a button, it will say run, and down here we're going to put this inside a loop if run is true. So if run, do this stuff. Okay? And if I run the program, here's this little button. It says run. When I click it, it runs. When I click it again, run, pause, run, pause. Now let's look again at the program a little bit more slowly. The key statement's this: it makes a button. It places it underneath that 3D canvas where the scene is shown. It has a binding. We say we bind this button to your function that you named run button. And when the user of your program clicks on the button, it will run this, it'll call this function and send to it a reference to the button itself. And one of the attributes of the button statement is text, and so you can look to see b.text initially had the value run, initially run was false, and so it took this else statement and set it to pause and set run to not run. And that means that down here, this if run statement will be running if you said to run, and it'll be paused if you said set to pause. So are there questions on this structure, which is a little bit fancy, but is also pretty easy to do in VPython, and it's typically not that easy to do in most programming environments. Questions about this? Okay. Then one more, well, actually, I lied. Two more things. I'm going to create a graph who's going to be about height of 200 pixels and has a title, and it has an X title and a Y title, and I'm also going to specify a curve object to appear in that graph. I guess I could close this up a little bit now. And then in the while loop, I'm going to add this statement. So Y is a G-curve object. That means it's going to be a red line graph on a graph. And Y.plot says for T is the abscissa and the ball's velocity, momentum over mass, as the ordinate, make a graph. And with those additions, what I get is this. And I can also have it, notice it's a live graph. Many graphing packages require that you have to keep track of all the stuff you want to eventually plot, and then you give it to them as an array. live graphs have their virtues in the sense that you can make connections between the behavior of the system in 3D and a graph of some important property of that motion. And then just for fun, I want to show you one other thing, which is fairly cool. I'm going to add in here the following. I'm going to create a local light. So VPython by default sets up some remote lights that illuminate the scene. You can make up your own lighting if you want to, and you can make distant lights like the sun, or local lights like desk lamp. And having created that light, I'm going to also make the ball be emissive, meaning it's going to glow, and we're going to keep tracking this local light to make sure it's at the same place as the ball is. So after updating the ball's position, we'll also update the local light's position, and now you get this pretty interesting effect. So that's a kind of an overview of all the different kinds of things that you can do with VPython. And of particular use, as Marco was hinting, is that if you have a 3D visualization, you have a very powerful visual check on your algorithm. And you can see things that you otherwise can't see. Some of you may have seen a seminar a colloquium that Ruth Shabai and I gave last year on the surface charge model of circuits, where we found indeed having a 3D visualization of the surface charges on a circuit, we learned things that other people, including us, had not known about how the charges pile up on the surface of the wires in a circuit. So it's very often the case that visualizations meant not just as graphs. Yes, graphs are important visualizations, but they're not the only kind of useful visualization. So I hope you found this interesting. I will give Marco a link to propagate to you of a location for this full program, and I'll entertain any questions.
I have a question.
I am wondering, it's kind of a silly request, is if we could go to line 13 and...
Sure.
Okay.
Yes.
And up the x part of the vector to 4. We might also need to make the floor a little longer if we do that, but I just wanted to see what it would look like. Okay, nice. Also, I noticed I did take a intro to electricity and magnetism with Dr. Shabai, and I thought this program was really cool.
Good. I'm glad you enjoyed it.
At first. Now it makes a lot more sense, and it's a lot more interesting at that. Yeah, she was great. And I know you guys, I saw your name all over the things that she recommended as well. There is this one little game I think you guys might have made where...
Electric field hockey.
Oh my, yes.
You go to matter and interactions.org/student. You will find there 70 VPython, GloScript VPython programs that include electric field hockey, which in 1992, Ruth Shabai got a national award for best educational software. It's a fabulously wonderful game, and she now has a 3D version of it that you'll find there, along with many other programs. Basically, you use you nail charges down on a rink, and you push charges into a goal around obstacles, and it's very cool. Here is that program again. but running in a Jupyter Notebook. Okay? So the syntax is the same. Okay? Other question?
So I have a nerdy question. On when you use when you want to write stuff, at least in GlowScript, I see that you are using HTML, right?
Well, so I'm sitting here in a browser editor named Ace.
Okay.
Okay, and the compilation leads to, as we saw, a JavaScript program.
And so JavaScript needs some sort of HTML format for the title. I mean, for the whatever you write, like X title, Y title, and stuff like that.
Oh, okay. So here's yes, exactly. So here's the titling of that graph actually used some HTML decorations.
Yeah, exactly. So how difficult would it be to have, like in Matplotlib, LaTeX integration, that you can write a LaTeX statement?
So there is something like that. So let me go to the help and work with 3D objects, LaTeX math displays.
Oh, excellent.
Now, but now this works in the GlowScript environment, but I think I haven't tested whether that works in Jupyter Notebook. It might, because we're just going to be sending stuff over there to be used over on the other side in the browser. But it, at least the GlowScript version of VPython supports MathJax, which supports LaTeX.
Yeah. Okay. Guys, any question for Bruce? Because not. Yeah, go ahead. Go ahead.
I have a question about the program, going back to it.
Yeah.
So you showed how to put in a run button and a pause button. Is there any way to put in like a rewind button?
Rewind?
Mm-hmm.
Oh, of course. Oh, you would put in a button which says labeled rewind. And when the user clicked rewind, you in the bound function, you would erase everything and start over.
Huh.
Sure.
Or even better, you can make a reverse button that goes back, and then you will have to change the sign of your velocity.
Just change the sign of DT and go backwards. Sure.
Yeah.
Absolutely.
Oh, okay.
It's a programming language.
I was looking at it and I was like, do you do just f equals negative vector? And then it's like, oh wait, there's the DT function there. So, thanks.
Yeah. I'll mention that if you have questions or suggestions or whatever, please write to me at brucesherwood@gmail.com or my UNT address. I am the lead developer of VPython. I have colleagues working with me on this in the two major versions, GlowScript VPython, we don't have to install anything, and Jupyter environment. Well, you can use idle, you can use Spider, you can use any Python launcher. There's a third environment, Trinket.io, very interesting place that supports kind of a junior version of notebooks with embedded GlowScript in it. It's very cool. And all three of these share the GlowScript library. So the core of it is the GlowScript library, but it's used in GlowScript.org, Trinket.io, and within the VPython module for Python.
So at this point, I would add for the class that if we go back to that program that does the static equilibrium and we look at it, after having seen how real VPython works, you realize immediately how inadequate is that way of programming it. I mean, we already did corrections or improvement to that code, but you see clearly how that particular version and how it is developed doesn't use any of these features of VPython. It basically calls every time something that does everything from scratch. There is no use of this natural language of VPython that allows you to just define the class sphere, and then the sphere will be moved depending on whatever is the model that you are using. And I mean, clearly it works in the way in which it's written, but it's not like elegant or effective. And here I want to make a point that is not that I encourage you to improve the codes that are given to you because I'm a fan of kind of elegance in coding. Is that a code that is badly written eventually will fail in terms of performance. It cannot be generalized because to generalize that code will require a lot of effort in adding things that are completely not necessary, and it will make it so complicated that at a certain point you don't know anymore what the code is really doing. So good practice programming is not just for the sake of having a beautiful code. It's also to have a code that is readable, that is generalizable, that is modular, and that runs faster, and that can be improved. So always keep this in mind. And so if you guys want to rewrite that code, adding these capabilities of VPython to make it work, and it might be actually easier to rewrite it than to add the modification that you need to add in order to have the solution of the model that you are supposed to do.
Let me add too that notice in this program, simple though it be, we created a box object, we created a sphere object, and then down in here in the loop we were changing the attributes, but we weren't making new objects. You think of making the objects up here as very similar to putting the main parameters at the front of the program, right? Where you define G and stuff like that, and you define the objects that you're going to be moving around, changing their color or size or whatever. It's kind of it's like that, and the code that you got from the Landau book is kind of awkward because it keeps having to do it all over again, as Mark was saying.
So, any other questions? If not, Bruce, thank you very much. That was very enlightening. I see that there are comments in the chat that thank you for having done this presentation.
I have a simple question.
Oh yeah, go ahead.
Oh yeah, I would say, can you modify the code where you have walls and ceilings into the box? Because you have the floor, right? So the walls around it, and then a ceiling above it.
Well, it's a programming language. You can do whatever you want, right? I mean, it doesn't know anything, but it can make things that you tell it to make. So you want to put, yeah, sure, of course. In fact, you want to see an example of that is right here. So here's a tiny little program that make a bunch of boxes that look like that. And of course, you can make these transparent or semi-transparent. They don't have to be opaque. Yeah. If you can think of it, you in principle can do it. Now, some things are harder than other things, obviously, but I do suggest that you spend a few minutes in the help at glowscript.org, just seeing all of the objects that can be made, although I suppose I could show the pictures to you right here. So you see we had arrows, boxes. You can clone objects to make more of them. You can compound objects. This is a cylinder plus a box. You can make cones and curves, extrusions. You can extrude a 2D object along a 3D path. Ellipsoid cylinders, helixes, very nice for making springs, labels that go in front of the scene, point objects that plot really fast if you have a large number of things to do, pyramids, rings, spheres, triangles, the fundamental unit of 3D graphics, 3D text, graphs, textures, opacity, lighting. Yeah. But it was a lot of fun. Thanks, guys.
Thank you, Bruce.